Okay, I've already hinted at this, but this is average and instantaneous acceleration. It's basically the exact same thing as velocity. It's just the next derivative and the same basic concept. Okay, so yep. Did you know average acceleration is the average rate at which velocity changes? And I think the next one, the average change in acceleration is jerk. And I know this because my friend for a while had a t-shirt that said, "Don't be a d cubed x d t cubed." Yeah, I have really cool friends, and I was like, so that means don't be a jerk. Um, so same thing, acceleration as a vector. I already kind of showed you how we did that. Here's a picture of a train. So this is really the I always look at these like, thanks for the picture of a train. So you can be moving forward, having forward velocity, but having negative acceleration. That means that you're going forward, but you're slowing down. Make sense? Okay. So if your acceleration is going the same direction as your velocity, you're speeding up. If they're going in opposite directions, you're slowing down, but you're still moving forward. Like you can be moving forward, but still slowing down. Okay, so that's kind of where we're going with that. Doop da doop da doo, da doop da doo, da doop da doop da doo. Okay, a racehorse leaves the gates coming out. What is its average acceleration? Okay, so since its initial velocity is 15, but it starts from rest and it's eventually at 1.8 seconds, but it starts at time equals 0. These are just slopes, dude. Like, please don't go memorize formulas because then you're not going to understand why they make sense. This is just a slope. If you were graphing this dude's velocity and you'd be like, his velocity is 0 at this time and his velocity is 15 at this time, what's the slope of 1.8 and 15? Okay, it's just rise over run. So, whatever, 15. Oh, look, his average acceleration is 8.3. Okay, meters per second squared, right? And that's because velocity is in meters per second and time is in seconds. So we have meters divided by seconds again. So we get seconds squared. Okay, so there's nothing super magic about this. It's just average acceleration. Okay, so don't. Look, it's a horsey. Otherwise, I would have had no idea what this problem was talking about. Um, well, that was a lot of discussion for this. Um, why is it trying to say that the average velocity acceleration is negative? Well, I wouldn't have bothered calling it negative, but sure. Um, the direction toward the west. I think it's just being kind of a toot. I personally wouldn't have worried about the negative sign because, but I guess since it said west, but anyway, I wouldn't care. Um, we're going to put all these in vectors anyway, and so whenever I put this in a vector, I'd be like, acceleration is equal to negative 8.3 I hat to show that it's going west. So there you go. Okay, significance. Check your understanding. Instantaneous acceleration. Again, it's the slope of the line, tangent to the curve. We're just going to keep taking derivatives of things. It's going to be amazing. Okay, so here's the functional form of the velocity. Okay, do you just mean you're writing the velocity as a function? Why do we have to call it the functional form of the velocity? All right, so to get an acceleration, we just take the derivative of velocity, dv dt. So ddt of negative 5t squared plus 20t. And yes, I'm doing the thing where I rewrite it in my order because I'm a pretty princess. So minus 10t plus 20. That's the acceleration. So acceleration in functional form, that makes it sound like other forms are dysfunctional. At equals negative 10t t plus 20. Look at that. That's so nice. Okay, now we want to find the instantaneous velocity at all those locations. I am fully capable of plugging in 1, 2, 3, and 5. So, okay, I guess I'll do it. A at 1. Look at that. 2. And this is where I'm going to do something wrong. 3. Look at me do math. And 5. Oh, this is where I will mess something up. Negative 15 plus 20 equals negative 30 meters per second squared. So that's all my instantaneous accelerations. Oh, that was find the instantaneous velocity. Oh, so the instantaneous velocity would have been of the original problem. So this is what I get for being a smarty pants and not actually reading. So I can also do velocity. Oh, and now my pen is being bad. Come on, bad pen. Take a deep breath, computer. Okay, sometimes we just got to get into Zen computer zone. Velocity at 1. 20 minus 1. No, 20 minus 5. 20 minus 5, I told you I can't do math, is 15. And the velocity at 2 is 40 minus, what is 5 times 4? 20. You get the point. You just plug stuff in, you get answers, and then you don't really know what's going on. Which is kind of unfortunate because that takes the fun out of it. Okay, interpret the results of them in terms of the acceleration of velocity. So let me show you something even better. Okay, so instead of doing this, I'm going to hop over to Desmos. I guess I could do this on my graphing calculator, but I like Desmos better. Desmos, the free graphing calculator. Beautiful free math. Okay. I'm just going to open my graphing calculator. This is desmos.com in case you've never desmosed. All right, so I've got a velocity with respect to time is 20t minus 5t squared. Okay. Velocity of t equals 20t minus 5t squared. Okay, so there's velocity. Okay, and so then acceleration is ddt of velocity. Okay, and then actually, if you wanted to, we could probably come up with what the actual position vector is because it's the integral. We haven't really gotten into this, but right, if velocity is derivative of position, then position is integral of velocity. 0 to, I don't care, to t. We'll just t of v of t. I never actually tried this. We're just going to see if it works. No. Okay, I'll just do it by hand. So it would be 10t squared minus 5 halves t cubed plus some unknown constant, which would be like your starting position. So we'll just say it starts at 0, right? If I take the derivative of this, do I get the thing below it? Oh no, this should be a 3. Okay. Well, this is a crazy picture now. But let's see what's actually happening. Okay, so my green is position. Red is velocity. Here, okay, let's just see if position makes sense. So my position is going forward with respect to time. Hold on. Oh, I think it's upset because I called this X. Maybe I'm going to call it cow. Or I'll call it R. There we go. Okay, it didn't like X. It was treating it like an X variable. There we go. Okay. So what we can see going on here is the position. Let's just, whoa, I've really got to go out. So it goes uppity, 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 up, and then it turns around. Okay, I wonder if I can fix the settings on this just to go from 0 to 10. I'm sure I can make X, oops, go from 0 to 10. Okay. Okay. So this is my position. The position goes up to here, and then he comes back here. So it takes him a little while, because this is time, to get up here. It takes them 4 seconds basically to max out. Okay. So what we're seeing with in terms of velocity is the velocity is slowly increasing and increasing and increasing. Now the velocity is still increasing, but the velocity is positive, 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 positive. Here the velocity is positive, but it's decreasing. Okay, so I'm going to say that again. Velocity positive, 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 but here the velocity is decreasing, which makes sense because this is like a turning point, right? Where it goes from concave up to concave down. That's that turning point right there at like 2 seconds. So right here at 2 seconds, it goes from like kind of, I want to say like not speeding up, but it's increasing, but it's not increasing as fast. And then it starts decreasing, but it's still positive. It's just not as positive as it used to be. And then it gets here and he starts to turn around. So the velocity goes negative. Okay, does that make sense? So here we have a negative velocity. Red is negative velocity to go with the position. Notice our position isn't negative. It's just that we've gone from a position 50 feet away back to where we began. And the way we do that is by moving backwards velocity. So now let's look at this one. This is a straight line. So we are continually we have an acceleration, we have a high acceleration, a slower and slower and slower and slower acceleration until our acceleration switches from positive to negative. Okay, does that make sense? So here our acceleration started high, but then, because this is the velocity, so we started going pretty fast and accelerating pretty fast, and then we started slowing down till here, which is when we started going, our acceleration, we started decelerating, which is what happens from here to here. And that's when this went from accelerating to decelerating, and we finally decelerated so much that we went into a negative velocity. Okay, and if that didn't make sense, that's okay. And there's probably other people that explain this way better. But for some people, seeing the graphs really help it make sense. Let me turn some of these off. But what you have basically are these critical points of things that are going on. So like here at time equals 2 is where it goes from under to over. So happy face to sad face. Happy face to sad face is whenever the velocity goes from going up to starting to go down. Whenever it maxes out here is when this crosses 0. So you might remember in calculus, you all did like graphing, or you talked about critical points. So that's what these critical points are representing, and that's why these graphs matter. Okay, so you might have more suggestion. You might have more success by taking some of these plots, putting them in Desmos and being like, okay, so what is physically happening? And I am not a person who understands things very well based on pictures. And so, I have to really, really talk myself through this. So just as an FYI, this plus just shifts the whole graph up or down. So, if the duck started 13 feet from the start line, then that's where that 13 feet would go. But I'm just starting the duck at the start line. So as the duck is, I don't know why he's a duck now, but as the duck is moving, his velocity continues to be positive. But I think where we get confused sometimes is that this is still positive velocity, even though it's not as positive as it was before. And the fact that it's not as positive as it was before is represented by the fact that the acceleration goes from positive to negative. So that was a whole lot of talk about something that I was like, oh, this is basically just the same thing we did last time. But maybe it'll kind of bring it to your brain a little bit better, help it make a little bit more sense. Let's see, is there anything else in this project I need to go into? Oh, no, look, see, they did that. That's pretty much, yep, okay, look at them. All right, okay, getting a feel for acceleration. Well, that's pretty silly. And yeah. Oh, look, I can click on something. Well, I can't click on it here because I didn't see if this actually works. Chirp. Runtime. Oh, it's a PhET simulation. PhET simulations are all the rage in physics education. The moving man is starting up. Meow. Meow.
Okay, I'm not learning anything from this, but maybe you will. Boop, 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 but I want to see the vector. Okay, I'm not entirely sure what I'm doing or why this. Okay, I'm just gonna be kind of snarky about this because it's kind of funny. I guess the idea is I'm gonna keep increasing my mouse speed to make it go this way. Now I'm gonna slow my mouse down. Yeah, okay. Meow. Okay. Well, maybe you can do something with this and discover, if nothing else, you can be like, somebody did this, but I can start slow and speed up. Okay. Science. Okay. That was unnecessarily fun. All right. I'm going to start the next video now.